And silicon chips are everywhere. They are in your phone, your car, your coffee maker. They are the brains of our modern world. For over 50 years, they've gotten smaller, faster, and cheaper. This incredible progress has been guided by a simple observation called Moore's Law. It basically says that the number of tiny switches or transistors we can cram onto a chip doubles about every 2 years. And for a long time, that's exactly what happened. We just kept shrinking them. More transistors meant more power. More power meant smarter phones, better computers, and the entire internet. But that party is ending. We are starting to hit a wall, a physical wall. The components on these chips are now so small, we are measuring them in atoms. When you get that small, the weird rules of quantum physics take over. Electrons, the little particles that carry electricity, start to misbehave. They can tunnel through barriers they shouldn't be able to cross. It's like building a fence to keep a dog in, but the dog can just walk through the wall. This leakage of electricity messes up the calculations. The chip stops working correctly. There's another problem, Heat. Imagine a city. As you cram more people into the same space, it gets hotter. The same thing happens on a chip. We are packing so many transistors so close together that they generate an incredible amount of heat. If they get too hot, they melt. We are already spending a huge amount of energy just cooling down our computers, especially the big data centers that run the internet. Can't keep making them denser and hotter forever. The energy bills would be astronomical, and the chips would destroy themselves. So, the industry is facing a huge question. What comes next? If we can't just keep shrinking silicon, what do we do? The answer isn't one single thing. It's not like we are going to throw away all our silicon factories and switch to a new miracle material overnight. The future is more complicated and honestly more interesting than that. It's a mix of three big ideas. First, we get smarter about how we use silicon. Second, we look for new materials to replace it. And third, we completely rethink what a computer even is. Let's start with the most realistic near-term solution, making silicon better. Just because we can't shrink transistors much more doesn't mean we can't be more clever in how we arrange them. For decades, computer chips have been like single-story buildings. We just kept trying to make the building wider and pack more rooms on one floor. The new idea is to build up. We are now stacking chips on top of each other, creating 3D structures. This is called 3D integrated circuitry. Think of it like building a skyscraper instead of a sprawling ranch house. You can fit a lot more on the same piece of land. By connecting chips vertically, the signals don't have to travel as far. Shorter travel distance means faster speeds and less energy used. It's a more efficient design. You might hear engineers talk about chiplets. This is part of that same idea. Instead of making one giant monolithic chip that does everything, which is very hard to manufacture without defects, companies are building smaller, specialized chiplets. One chiplet might handle processing, another might handle memory, another graphics. Then they are all packaged together, sometimes stacked, to work as a single unit. It's like building with high-tech Lego bricks. This approach is cheaper, more flexible, and lets companies mix and match the best parts for a specific job. Another way we're getting smarter is by designing specialized chips. For a long time, the main chip in your computer, the central processing unit or CPU, was a generalist. It was designed to be pretty good at everything, from running a spreadsheet to playing a video. But being a generalist means you aren't a master of anything. Now we are seeing a boom in specialized hardware. The most famous example is the graphics processing unit, or GPU. It was originally designed to render graphics for video games. It did this by being really good at doing thousands of simple calculations all at the same time in parallel. It turns out that this kind of parallel processing is also perfect for training artificial intelligence. That's why companies that make GPUs are now at the center of the AI revolution. They didn't invent a new material, they just found a new, incredibly powerful way to use the silicon they already had. We now have chips designed specifically for AI, called TPUs, Tensor Processing Units, or NPUs, Neural Processing Units. These chips are stripped down to do one thing, AI math, and they do it with incredible speed and energy efficiency. Your new phone likely has one of these inside. It helps with things like recognizing your face or understanding your voice commands without having to send data to the cloud. This trend of specialization will continue. We'll see more custom chips designed for specific tasks working alongside a general-purpose CPU. The future is a team of specialists, not a single hero, but even these clever tricks can only take us so far. Eventually, we will exhaust what silicon can do, no matter how we stack it or specialize it. That's when we will need to move to the second big idea, new materials. This is where scientists are looking for a true replacement for silicon, something that can be made even smaller and work even faster. The most famous candidate is graphene. You have probably heard of it. It's a sheet of carbon atoms arranged in a honeycomb pattern, and it's only 1 atom thick. It's the thinnest material known to man. It's also incredibly strong and an amazing conductor of electricity. Electrons can zip through it with almost no resistance. In theory, this means graphene transistors could be much smaller and switch on and off much faster than silicon ones, perhaps hundreds of times faster. It sounds perfect, but there's a huge problem. To work as a transistor, a material needs to not only conduct electricity, but also be able to stop it. It needs an off switch. In technical terms, it needs a band gap. A band gap is an energy barrier that stops electrons from flowing. Silicon has a great band gap. You can easily turn it on and off. Graphene in its natural state has no band gap. It's always on. This makes it a terrible material for a digital switch. Scientists have been working for years to engineer a band gap into graphene by cutting it into tiny ribbons or doping it with other chemicals. They have had some success in the lab, but it's been incredibly difficult to do this reliably and on a mass scale. Manufacturing perfect. Large-scale sheets of graphene is another massive hurdle. So while graphene is a wonder material, it's not ready to replace silicon in our CPUs anytime soon. Another carbon-based material getting a lot of attention is the carbon nanotube, or CNT. You can think of a CNT as a sheet of graphene rolled up into a tiny tube. Like graphene, CNTs are incredibly strong and great conductors. And unlike graphene, they can be made to have a band gap, which means they can be used to make transistors. Researchers have actually built working computers using CNT transistors in the lab. They are still very basic, nowhere near the complexity of a modern silicon chip, but they prove the concept works. The challenge, again, is manufacturing. Imagine trying to build a city where all the buildings have to be made from trillions of perfectly aligned, identical microscopic tubes. It's a nightmare. We need ways to grow and place these nanotubes with near-perfect precision. We are not there yet, so if carbon is proving tricky, what else is there? One group of materials that looks promising is called transition metal dechalcogenides, or TMDs. That's a mouthful, but a key example is a material called molybdenite, or MoS2. Like graphene, it can be made into sheets that are only a few atoms thick. But unlike graphene, it has a natural, excellent band gap. This means it can be used to make very small, very efficient transistors. In theory, TMDs could be the answer, but we are in the very early days of research. We are still figuring out the basic properties of these materials and how to produce them in high quality. The road from a promising lab result to a billion-dollar fabrication plant is a very long one. Another material worth mentioning is gallium nitride, or GaN. You might actually own a piece of this future already. Many new, smaller phone and laptop chargers use GaN instead of silicon. GaN is what's called a wide bandgap semiconductor. This means it can handle much higher voltages and temperatures than silicon. That's why it's great for power electronics. It makes chargers smaller and more efficient because they waste less energy as heat. Some people think GaN could also be used for high-frequency chips, like the ones used for 5G and future 6G networks. However, it's currently much more expensive and difficult to work with than silicon, so it's unlikely to replace silicon for general-purpose CPUs. Instead, it will likely find its place as another specialist material in our technological toolbox. The search for new materials is slow and difficult. It requires breakthroughs in physics, chemistry, and engineering. And even if we find the perfect material, we then have to figure out how to build an entire global industry around it, just as we did with silicon. This brings us to the third, and most radical idea: what if the problem isn't the material, but the computer itself? What if we need to completely rethink how we compute? This is where we get into new computing paradigms, ideas that move beyond the simple on-off logic of today's digital computers. The most famous of these is quantum computing. This is a technology that gets a lot of hype, and it's important to understand what it is and what it isn't. A normal computer uses bits. A bit is a simple switch. It can either be a 0 or a 1. All the complex things your computer does are built on top of this simple binary logic. A quantum computer uses something called a qubit. Thanks to the strange rules of quantum mechanics, a qubit can be a 0, a 1, or both at the same time. This is called superposition. Furthermore, multiple qubits can be linked together in a phenomenon called entanglement. When qubits are entangled, the state of one instantly affects the other, no matter how far apart they are. This ability to exist in multiple states at once and be interconnected allows a quantum computer to explore a vast number of possibilities simultaneously. For certain types of problems, this provides a staggering advantage. A quantum computer will not replace your laptop for browsing the web or writing an email. Classical computers are great at those tasks, but for very specific, complex problems, a quantum computer could be revolutionary. These problems include discovering new drugs and materials by simulating molecules in perfect detail, a task that is impossible for even the most powerful supercomputers today. They could also be used to solve complex optimization problems, like improving financial models or making shipping routes more efficient. And famously, a powerful quantum computer could break much of the encryption that protects our data online. But building a useful quantum computer is one of the hardest engineering challenges ever attempted. Qubits are incredibly fragile. The slightest vibration or change in temperature can destroy their delicate quantum state, a process called decoherence. This is why most quantum computers have to be kept in huge refrigerators that are cooled to temperatures colder than deep space. They also require a huge amount of overhead for error correction. For every qubit that does useful work, you might need hundreds or even thousands of others just to make sure it's working correctly. We are still in the very early days, like the 1940s of classical computing. We are building machines with dozens or hundreds of qubits, but we will likely need thousands or millions of stable error-corrected qubits to solve real-world problems. Quantum computing is coming, but it will likely exist as a specialized cloud service or a coprocessor for specific tasks, not as a device on your desk. Another radical new approach is neuromorphic computing. This idea is inspired by the most powerful and efficient computer we know, the human brain. Our current computers are based on something called the von Neumann architecture. In this design, the processor and the memory are separate. Data is constantly shuttled back and forth between them. This von Neumann bottleneck consumes a lot of time and energy. The brain works differently. In the brain, processing and memory are intertwined. Neurons and synapses store information and compute with it at the same time. The brain is also massively parallel. Your billions of neurons are all working at once. And it does all this while running on about 20 watts of power, less than a light bulb. A neuromorphic chip tries to mimic this structure. It builds artificial neurons and synapses in silicon. Instead of processing information in a linear, clock-driven way, it works more like a real brain, with signals firing and creating cascades of activity when it receives input. These chips are not designed to be good at the kind of precise step-by-step math that a CPU excels at. You wouldn't use one to calculate your taxes, but they are incredibly good at the kinds of things brains are good at learning, recognizing patterns, and dealing with messy, real-world data. They are extremely energy efficient. A neuromorphic chip could power a small drone that can navigate its environment by sight, or a medical sensor that can analyze a heartbeat in real time, all while running on a tiny battery. It's a completely different way of thinking about computation, one that is more about perception and adaptation than raw calculation. Like quantum computers, neuromorphic chips won't replace CPUs. They will be another specialist tool, an AI coprocessor that works more like a biological brain. Let's go even further into the future. What about using light instead of electrons? This is the idea behind optical computing. Light travels much faster than electrons through a wire, and photons, the particles of light, don't interact with each other in the same way electrons do. This means they generate much less heat. An optical computer could, in theory, be incredibly fast and energy efficient. We already use light to transmit data over long distances through fiber optic cables. The challenge is to get light to do computation on a microscopic scale. We need to create the equivalent of a transistor for light and optical switch that can be turned on and off by a single photon. We also need to figure out how to make light beams interact to create logic gates. People are working on this using tiny structures called photonic crystals and waveguides to steer light around a chip. But it's extremely difficult. Building an all-optical computer is a distant dream. A more likely scenario is a hybrid approach, where optical components are used for communication within a chip or between chips, breaking that von Neumann bottleneck by moving data at the speed of light. And for the most futuristic idea of all, we have biological computing. This involves using the machinery of life itself to store and process information. The most well-known example is DNA computing. A single strand of DNA is a code, a sequence of 4 molecules, A, C, G, and T. This is a very dense way to store information. It's been estimated that you could store all the data generated in the world in 1 year in about a kilogram of DNA. It's also incredibly stable. DNA can survive for thousands of years. But DNA can also be used for computation. By designing specific DNA strands, you can get them to react with each other in a test tube to solve a mathematical problem. The real power here is massive parallelism. You can have trillions of DNA molecules all working on the problem at the same time. In 1994, a computer scientist used this method to solve a classic computational problem. The downside? It was a very simple problem, and it took him days of work in a lab to get the answer. DNA computing is incredibly slow. Setting up the problem and reading out the result takes a long time. So it's not for speed, but for problems that require checking a huge number of possibilities and where time is not the most critical factor, it could one day be a viable option. It's a field that's still in its infancy, but it shows how far we are willing to look for new ways to compute. So, what is the next step after silicon chips? The real answer is that there isn't one single next step. The future of computing is not a replacement, it's an expansion. For the next decade or so, silicon will still be king. We will just use it more creatively with 3D stacking and an army of specialized chips for AI, graphics, and communications. The era of the general purpose CPU doing all the work is over. We are moving into an era of heterogeneous computing, where different types of processors work together as a team. Looking further ahead, we will start to see new materials creep in. Perhaps we will solve the manufacturing problems of carbon nanotubes, and they will begin to replace silicon in high-performance processors. Or maybe a TMD material will prove to be the winner. Gallium nitride will continue to dominate power electronics and high-frequency communication. The material science is advancing, but it's a slow and expensive process, and woven into all of this will be the new paradigms. We will see dedicated quantum processors, likely accessed through the cloud, tackling problems in science and optimization that are completely out of reach for classical machines. We will have ultra-low power neuromorphic chips in our edge devices, our phones, sensors, and robots, allowing them to learn and interact with the world in more intelligent ways. We might even have hybrid chips that use light for communication to achieve incredible bandwidth. The future of computing is a toolbox, not a single hammer. The right tool will be used for the right job. Your future device won't just have a chip inside it. It will have a system. A silicon CPU might act as the general manager delegating tasks. It will send a graphics-intensive task to the GPU. It will hand off a pattern recognition problem to the neuromorphic coprocessor. And for a truly monstrous optimization problem, it might send a query to a quantum computer in a data center thousands of miles away. This is a much more complex and fragmented world than the one we've lived in, the one dominated by Moore's law and the steady, predictable march of silicon. It presents huge challenges in software. How do you write programs that can efficiently use all these different kinds of processors? But it also opens up incredible new possibilities. By moving beyond the one-size-fits-all model, we can continue to push the boundaries of what is possible. The end of Moore's law isn't the end of computing. It's the end of computing's childhood. It's the point where things get complicated, diverse, and truly interesting. The simple path of just making things smaller is over. The new path requires us to be more creative, more specialized, and more willing to explore the strange new worlds of quantum, neural, and optical computing. The road ahead is not a single clear highway. It's a branching set of trails into a new and exciting frontier.